So far we talked about resistors in series, resistors in parallel, and the combination of parallel and series resistors. And we talked about capacitors in series, capacitors in parallel, and combination of capacitors in series and parallel. And then we talked about the combination of capacitors and resistors, which we call RC circuit. And we saw the time constant for RC circuit. And then we also saw how charge is accumulated in RC circuit. So that's the RC circuit. When you charge this RC circuit, you will accumulate charge on the capacitor, which is given by E times C, 1 minus E minus T over RC. Okay. So let's talk about where we use capacitors and RC circuit. So what are some of the applications? So we'll focus on the application of capacitors. So most of the electronic devices that we use in our modern life have RC circuit. Okay, they have capacitors, resistors. Like for example, this keyboard. This keyboard works on the principle of charging of capacitor. All these keys, they have capacitors under it. Okay, so when you hit the keys, they store different amount of charge in the capacitor. So each key has different capacitance, and depending on how much charge is stored in the capacitor, it sends the information to the CPU of the computer, and the computer knows which key you pressed. Okay, so for example, this key may have different capacitance or different amount of charge stored when you press it. When you press the other key, it may store different amount of charge. When you press this one, it may store different amount of charge. So depending on how much charge is stored, the computer knows which key you pressed. Okay. Likewise, in medical applications, you use defibrillators. Defibrillator is also kind of capacitor. So when people have irregular heartbeat due to some condition, they use the defibrillator to briefly stop their heart, and then when they stop the defibrillator, the heart goes back in the same normal beating. Okay, so that's the application of capacitor. And in human body also, we have natural capacitors, natural RC circuit. Like we have these nerve cells. So nerve cells could be modeled as capacitors or RC circuit with capacitor as well as resistors. So you saw some of the examples in the homework and worksheet last time, where you calculated the capacitance of cells, because in cells there is charge or potential difference on outside and inside the cell. So you have across the cell membrane, you have this cell membrane. So you have positive on one side of the outer part of the cell membrane and negative on the inner part of the cell membrane. So this cell membrane also acts as a capacitor, because the function of capacitor is to separate or store charges. Okay, one type of charge on one side and the other type of charge on the other side. So your cell membrane acts as a capacitor. And in some cell membranes, it not only have capacitor, but also it can have resistor. So it will act as RC circuit, this one. Okay, this is RC circuit that has both capacitor and resistor. So let's talk about that. Let's see, where is my PowerPoint. What happened to my PowerPoint? So here is a simple model of nerve cell. Okay, so the model of nerve cell begins with a cell membrane. So we have the cell membrane. Let's see if I can use pen. So that's our cell membrane. This whole thing is the cell, nerve cell. That's cell. Membrane. And the cell membrane is about 7 nanometer thick. This is about 7 nanometer thick. And there is conducting fluid inside and outside the cell membrane. So this inner part has conducting fluid, and the outer part also has conducting fluid. So the in this cell membrane, the ions are the charge carriers. In our RC circuit, when we talk about the flow of current, the electrons are the charge carriers. Basically, charge is carried by electrons from battery to capacitor and back to the battery. Okay? So electrons are the charge carriers. But in case of cell membranes or nerve cells, these ions, sodium and potassium ions, are the charge carriers. And there are also other ions, but sodium and potassium are the dominant ones. So that's why we will only focus on sodium and potassium. So we will not consider other ions, just to make the discussion a little bit more simpler. Okay. So there is this ion exchange pump in the cell, which acts as a battery. Okay. So this is similar to a battery. Basically, it pumps potassium ion into the cell and sodium ions out of the cell, and that pumping maintains the difference in the charge. So because of this pumping, you will have positive charge on outside the cell and negative on inside the cell. Okay. So because of this charge separation, there is finite EMF or potential difference. We know potential difference or EMF is due to the separation of charge. You have a bunch of positives on one side and bunch of negatives on other side. The difference in the charge produces EMF, which we also call delta V. So there is delta V inside the cell membrane because of this charge separation. Okay, and whenever there is delta V, there is also electric field, because electric field and potential difference are two sides of same coin. If you have potential difference, you have electric field. If you have electric field, you have potential difference. They are connected to each other. And we know the formula for electric field in terms of potential difference, how they are related. So it's delta V over D. Okay. So if I want to find electric field, then I just divide delta V, potential difference, by D. I get the electric field. So there is electric field inside the cell membrane. Okay. And the potential difference of the cell is called resting potential or membrane potential, which is about 70 millivolts. So this is the membrane potential. because it's the potential difference across the cell membrane. So that's membrane potential. It's also called resting potential because that's the initial potential without any stimulus. And if you measure the electric field inside the cell, the electric field is 0. Also, electric field outside the cell is 0. But in the cell membrane, it is not 0. Okay? There is finite electric field because there is this positive charge on the outer part and negative charge on the inner part. So there is this potential difference, and the potential difference creates the electric field inside the cell membrane. So and usually we measure the resting potential or membrane potential of the inner part of the cell. Okay? So we measure the inner part of the cell's potential difference. That's why usually the resting potential is negative. Okay? Negative means we are considering this to be the potential that we are considering. So negative 70 millivolts. So like I said before, if I want to know this electric field E of the cell membrane, I can find that by using this formula. So for resting cell membrane without any stimulus, the electric field is given by delta V over D. Delta V is 70 millivolts, which is that, 70 times 10 to negative 3 volts. And D is the thickness of the cell membrane, which is 70 times 10 to 9, 10 to negative 9. Let's see if I recorded. Okay. And if you do the calculation, you get that number. That is the electric field, which is really, really large number. Okay, if you produce that much electric field in air, that could produce a spark. Okay, it's a really big electric field inside the cell, in cell membrane. And we also need to specify the direction of the electric field. So the direction of electric field is always pointing from positive to negative. Okay, so that's the direction. You see that arrow. So because the outside of the cell has positive and inside of the cell has negative, so the cell membrane acts as a capacitor. So that's the capacitor. We are modeling the cell membrane as a capacitor, and it also has some resistance. Okay, it offers the ions cannot easily go in and out of the cell membrane. It provides some resistance. So we can also model cell membrane as a resistor. So it has both capacitance and resistance. Okay. Now, what happens when the cell membranes are introduced with some kind of stimulus? Okay. For example, you touch fire or someone touches you. So what happens? So whenever it comes in contact with some kind of stimulus, these sodium channels open, and the sodium channels allow the sodium ions, usually sodium ions are outside, they enter the cell through the sodium channel. Okay, and that increases the membrane potential. Okay, so this triggering of potential or increasing of potential is what we call action potential, and it is due to the stimulus, due to the response to the stimulus. Usually it increases up to 40 millivolts, goes from negative 70 all the way to 40 millivolts. Okay, and this process is what we called depolarization. So here, let's see. Here, the cell is in polarized state. So this is polarized state, polarized cell. Positive on outside, negative on inside. So that's polarized state. And switching off the signs, positive and negative, is what we call depolarization. Okay, so here there is depolarization of charge. And it's because of the movement of sodium ions from outside to inside. And then after some time, after a brief time, the potassium channel opens, and these potassium channels go out of the cell. They go out, and then the cell repolarizes. This is repolarization. P-O-L-A-R, repolarization. Okay. That means now again we have positive on outside and negative on inside. Okay. So repolarization is done by exchange of sodium and potassium. So in the beginning we have sodium ions outside, but now we have potassium outside and sodium inside. Okay. And when there is a repolarization, this goes down. Okay, it overshoots to about negative 80 millivolts. It goes all the way to negative 80 millivolts during the repolarization. Okay, and there is some diffusion of the ions, and that brings it back to 70 millivolts through the slow diffusion process. So there is slow diffusion of sodium and potassium ions that brings back to 70 millivolts. Okay. And then now we have potassium outside and sodium inside, and we know there is this pump, and this pump will again maintain the same kind of ions inside and outside. So it will exchange the potassium and sodium through the pumping, through the this ATP process. Sodium ion would be moved out, potassium would be moved in. Okay, and it again it maintains the potential. Okay, so this is in response to stimulus. Now, how signals are transmitted from brain to muscle? So the signals are transferred from brain to muscle through the neurons. That's the neuron, and neurons have these parts. They have dendrites. These branches are called dendrites. There is this whole structure called cell body, which has nucleus. This part is nucleus. This whole thing is cell body. And this wire is called axons. Axons are the main parts that transmit the signal. The axons that go, or the neuron that goes from brain to the muscles are called motor neurons. Okay, so this is the motor neuron. There is also sensory neuron that brings the signal to the brain. So these axons are wrapped in something called this myelin sheath. Okay, these things are insulated myelin sheath, and they are made up of specialized cells called Schwann cells. Okay, so they are made up of that special kind of cell. And there is also this gap between these myelin sheaths. Okay, so these gaps are called nodes of Ranvier. So we have these gaps. Okay. So how signals are transferred? Through axons. So the signals are generated at the cell body, okay, and they are transmitted. The signals are transmitted through the axons, and the axons have these channels. Okay, they have sodium channel and potassium channel. So these are sodium and potassium channels. Oops, what happened? Okay, so it starts with the depolarization of the cells. Okay, so this is the depolarized cell. The depolarization causes the rise in the potential. So it goes from negative 70 millivolts to negative 40 millivolts. That's what we saw before. Okay, and this depolarized cells or depolarization moves along these axons. Okay, so this becomes depolarized, and then that causes the depolarization of this front one. So you see here now this part is depolarized, and this repolarizes. After the repolarization, it goes down again to negative 70 millivolts. So this part is depolarized, and then this depolarized part depolarizes the other part ahead of that. So here this depolarized is depolarized part, depolarization moves forward, and then this part again repolarizes. So there is this transfer of depolarization along this axon. That's how it transfers the signal. Okay, so basically these ion channels are mostly concentrated at these nodes of Ranviers. Okay, so this is the node. You see these channels are all focused on, concentrated at nodes of Ranvier. Okay, and because we have these channels at these nodes, so, and we also know these channels cause the potential difference inside and outside the cell. That's what we saw here, right? So in the very first picture, these channels and the pump causes the separation of the charge. This delta V comes from exchange of the charge through these channels. That means these channels are the source of potential difference. So that's why we can model this part, okay, the part where there is high concentration of ion channels, as battery, because battery produces potential difference. Battery is the source of potential difference. So we can model those channels as batteries or source of potential difference. And the axon, the inner part of the axon, have conducting fluid, and the conducting fluid offers some resistance to the movement of ions. Okay, so we can model the conducting fluid as resistors. So it offers some resistance. So we can consider that part to be a resistor. And myelin sheath can be modeled as capacitor. Okay. There is accumulation of charge on inner part and outer part of the myelin sheath. So we can consider the myelin sheath to be a capacitor. So that means we can consider this part of the axon to be an RC circuit. RC circuit has a resistor and a capacitor, sorry, this capacitor, and it is connected to a battery. Okay, and when a stimulus hits this part, the ion channels open up and they transfer the ions, causing some finite potential. Okay, and whenever there is finite potential, that closes the switch, and that triggers this RC circuit. So whenever there is closing of this switch, there is flow of current. In this case, the flow of current is flow of sodium ion and potassium ion. So there is flow of sodium and potassium ion through this circuit. This is just a model. Okay, there is no actual circuit in the axon. So that's just the modeling of this part. So there is flow of this sodium and potassium ion along this circuit, and there is accumulation of these sodium and potassium ions on the myelin sheath, okay, as just like the accumulation of charge in a capacitor. Okay, and we know in RC circuit, if you remember from our previous discussion, RC circuit is characterized by its time constant. There is a constant called time constant. If you guys remember, time constant is the time it takes to charge the capacitor by 67%, its maximum value. Okay, so it's the time to charge a capacitor in the RC circuit by 67% maximum value, 67% Q maximum. So this RC circuit also has its characteristic time constant, during which this would be 67% full. So once it's 67% full, this part will trigger the adjacent part. Okay, this part will trigger the next RC circuit. So it has this line of RC circuit. So we have RC circuit here, RC circuit here, RC circuit here. So it's continuous RC circuit. So when this one reaches 67% full Q max, it will trigger this one. Now this one will close, and then there will be flow of ions in this circuit, and that will fill the capacitor. And when this one reaches again 67%, it will trigger the next one. And when the next one reaches 67%, it triggers the next one. So that's how signal is transferred from one part to the next part of the axon. Okay, and that means to reach the signal from this part to that part, it takes time constant tau. Okay, so during time constant tau, the signal gets from point A to point B, because it takes that much time to get this one fully charged, and once it's fully charged, it triggers the next one. So it takes that much time to transfer the signal from one part to the other part. Okay, so that's what you see here. So this is the stimulus, some kind of stimulus. So that in this case, we are talking about the signal sent by the brain, actually. So this is the signal sent by the brain. The signal travels through each of these myelin sheath and the axons. Okay. So how rapidly does a pulse move down the myelinated axons? That's what we just saw here. So how fast? So we want to know what's the speed at which signals transfer from one part of this RC circuit to the next part of the RC circuit. We want to find the speed. Okay, so we just learned that it takes time t to get the signal from this part to that part, okay, and that's this t is time constant, and we know the formula for time constant. If you were in the lab last time, or if you were in the lecture last time, we calculated this this time constant. Time constant is given by RC. Okay, so that's the time constant. Time constant is R times resistance times capacitance. Okay, and the resistance of the axons between the nodes is 25 mega ohm. Okay, so this resistance is usually 25 times 10 to 6 ohms. Mega means 10 to 6 ohms. Okay, and the capacitance is, this capacitance is usually about 1.6 picofarad. Pico means 10 to negative 12 farad. So using those values, so this R, that's C, the time constant is about 40 microseconds. So it takes about 40 microseconds. That means it takes about 40 times 10 to negative 6 seconds to transfer the signal from point A to point B. Okay. Now we want to find the speed, okay, not just the time. So what's the speed? Speed, we know from basic physics, speed is defined as distance over time. Okay. And the distance between the two nodes, from this node to this node, from point A to point B, that distance is about 1 millimeter. Okay, so 1 millimeter is the distance, and the time to get from point A to point B is 40 nanosecond. Sorry, not nano, microsecond. That's the time. So distance over time, 25 meters per second. So that means the signal travels at 25 meters per second in the neurons. That's pretty fast. Okay, in 1 second the signal travels 25 meters. It's not super fast, but it's still, yeah, faster than the person can move physically. Okay, so that's the application of RC circuit in human body. So we'll talk more about capacitors and resistors in next chapter. We still have to talk more about these things in alternating current. So we will be talking about alternating current. This is the direct current. Direct current is the current where the value of current doesn't change with time. So you have, if you plot current versus time, the one we are talking right now, the current, it remains same. Okay, it doesn't change. So that means if you connect a battery to a circuit resistor, the current coming out of the battery is constant. If you get 0.2 amperes current, all the time you get the same current. Okay? It doesn't change. Same thing with the potential. So if you plot potential difference delta V of the battery versus time, the potential difference of the battery always remains constant. Okay, it's always, let's say, 1.5. But later we will talk about alternating current, where you will have a different source, not battery. Okay, not battery. We will have alternating current, where current will change with time. You will see current fluctuating like that, and you will see potential difference also fluctuating like that. So that's different kind of current, which is the current what we use in our power outlet. Okay, so that's when we talk about these types of currents, we will also come back to capacitor again. So for now, that's all for our direct current. So let's look at some of the multiple choice questions for the conceptual part. Let's see, where is my So let's look at this question. We have a tube filled with salt water, and you pass the current through the salt water by connecting it to a battery, and it is connected to an ammeter. Ammeter is a meter that measures the current. So the question is, what is the direction of conventional current in the salt water? Conventional current is the flow of positive charge. Okay, the flow of negative charge is the usual current direction, but we use conventional current to denote the direction of current. So which way the current, conventional current flow in the salt water? To the right or to the left? It's pretty straightforward, right? The battery is positive on this side, so it pushes the positive ions to the left, right? Positive pushes the positive. So positive charges move along the pipe from right to left, right? These positive charges. Whenever you see conventional current, that means it's the flow of positive charge. Okay? And throughout the circuit problems, we use conventional current, flow of positive. We don't talk about flow of negative. Okay, so this is interesting question. So let's look at this question. So you have three circuits, circuit 1, circuit 2, circuit 3. There are light bulbs, so that's light bulb. That's light bulb. That one doesn't have light bulb. And this is ammeter. The function of ammeter is to measure the current. Okay, it does not consume any power, or in other words, there is no potential drop across the ammeter. If you measure the potential difference, you will not see any potential difference across that. You will only see the potential difference on the battery, on the bulb. Okay, so ammeter is inactive component. It doesn't contribute to anything in the circuit. Okay, you can just assume that there is a wire. Okay, there is a wire. It doesn't do anything. This thing doesn't do anything. You can replace this with a wire. The only function is to measure the current. Its function is to measure the current, but it doesn't do any other contribute to other things. So the question is, rank all the three ammeters in order of their current measurement. So meaning, which one will have the current from highest to lowest? Okay, greatest to the least or smallest. So this one current, this is measuring current. So there is current in this circuit, current. There's current in this circuit, current in this circuit. Let's call the current in this circuit by A1. Current in this circuit is A2. Current in this circuit is A3. So which current will be the greatest and which current will be the smallest? They are same? These two have same current, that's right, because you have same light bulb, right? So they have same current, but there is no light bulb here. Light bulb means it's a resistor. Okay, resistor means it's trying to oppose the current. Okay, greater the resistance, less is the current. So let me write it here. Greater the resistance, less is the current. So that's the thing you need to consider. So with that, let's look at the question. Same resistance, okay, same resistor, so same resistance, same current. Comparing these two, which one has greater resistance? There is no resistor here. That means this one has the least amount of resistance. Least amount of resistance means the most amount of current, right? That means A3 will have the greatest current, and then A1 and A2 will have the same amount of current, right? Because they have the same resistance, so they will have same current. But this one would have the greatest current because there is no resistance, because nothing is obstructing the current, flow of current. So that means, let's see which one. A1 and A2 are equal, but they are less than A3. So F is the right answer. Okay, let's look at this one. We have 3 circuits. And we have 5 light bulbs. So out of those 5 light bulbs, rank in order from brightest to the least bright. So look at the question and think about it. Okay, so let me put the question here, and then I will see your answer. So which one you are saying? Which one? Say the number. Which A, B, C? Which one is F? This one? This one? Okay, so let's look at that. See if that is right or not. So these light bulbs have same resistors or resistance. Okay. So we know this thing. So more resistance means less current, and the brightness of the bulb depends on the current. Okay, brighter the bulb means more the current. Brightness depends on the amount of current. More current means brighter the bulb. So that means we need to think about the current. So this one has the resistors in series, and we know that when we combine the resistors in series, the resistance add up. Okay, the total resistance is greater. So this one has the highest resistance, because in series you add the resistors. Here, when you combine the resistors in parallel, what happens to the total resistance? Do they increase or decrease? Does the resistance increase or decrease? So the current is flowing to the battery when it sees 2 resistors. Now it has 2 paths. Okay, so it will have less resistance. So that means in this case there's less resistance. Resistance decreases whenever you combine the 2 resistors in parallel. Okay. What I mean is, if you have 2 resistors, let's say 2 ohm and 2 ohm in parallel, so the equivalent resistor is given by 1 over 2 plus 1 over 2. 1 over 2 and 1 over 2 is 1. So R is 1 ohm. Okay, so that's the equivalent. Each one has 2 ohm, but its equivalent is only 1. That means resistance decreases when you combine it to parallel combination. And when you combine them to series, you increase that, because if you have 1 and 1 here, total would be 2. Okay, so that means this circuit will have greater resistance, means least current. Okay, and the current flowing through each bulb is same, because if there is I flowing through that, this will get I, and this will also get I, because whenever the things are in series, they get the same current. Okay. Now this one has the less resistance than this one. That means if there is current I, actually let's consider there is current I through this. If there is current I through this, because there is half as much resistance in this, that means there will be twice as much current. Okay, less the resistance, more is the current. So compared to this first one, this one has half as much resistance. That's why I have twice as much current. So I have 2I, and we have two paths for this current to flow, and half of that current will go through this and half will go through this. So each bulb will get I and I. Okay, I need to go back to this one again, okay, because I didn't use the right number here. So I'll go back to that again. So let's not consider I here. Okay, so now let's look at this one. So compared to this one, the resistor here is twice as much. Okay, because we have two bulbs, so resistor is twice as much. That means there would be half as much current as this one. So if there is I here, the current here would be I over 2, because there is more double resistance, so half as much current. And in series, we know current is same everywhere, so this one will get I over 2, this one will get I over 2. Okay, whereas in this case, the combined resistors is half as much. That means there will be twice as much current produced by the battery, and out of those twice as much current, half will go through that, half will go through that, so each get I and I. So now you compare the brightness. Brightness depends on current, so current is I here, and I here. So all these three bulbs will be equally bright, and these two would be least bright. They are equally bright but less bright than A, D, and E. Okay, so ranking, A will be equally bright as D and E, because they have same current, and then those would be brighter than B and C, but B and C are equally bright. Okay, that's the ranking, which is A, D, E, B, C. Yes, so you're right. So that's the E. Okay, so E is the right answer. A, D, E, B, C. Yes. Okay, I think that's all for now. We are out of time. We'll continue this next time.